Imagine a scientist observing a strange signal on a screen. The wave rises and falls in a complicated pattern, almost like chaos. At first glance, there seems to be no clear structure hidden inside it. But scientists began to wonder something profound. Could this complicated motion actually be built from simpler pieces? This question would eventually lead to one of the most important discoveries in mathematics and physics, the Fourier Transform. Researchers discovered that the simplest repeating motions are sine and cosine waves. These waves are smooth, regular, and perfectly periodic. Some oscillate slowly, while others vibrate rapidly. The speed of repetition is called frequency. Just like a pure musical note contains a single tone, each sine wave represents one pure frequency. Scientists realized that these simple waves could serve as the fundamental building blocks of much more complicated signals. Now imagine a symphony orchestra. A violin produces one frequency, a flute contributes another, and drums create deeper vibrations. Each instrument is simple on its own, but together they create rich and complex music. Signals behave in the same way. A complicated waveform can actually be formed by combining many simple sine waves with different frequencies and amplitudes. What appears chaotic may simply be many simple patterns layered together. The French mathematician Joseph Fourier proposed a revolutionary idea. He claimed that any sufficiently well-behaved signal could be decomposed into sine and cosine waves. This became known as Fourier analysis. Instead of studying how a signal changes over time, Fourier's method asks a different question. Which frequencies are hidden inside the signal? This shift in perspective transformed mathematics, physics, and engineering forever. Suppose a signal contains two hidden frequencies. In the time domain, the signal looks blended and difficult to interpret. But the Fourier transform separates the mixture into its individual frequency components. Suddenly, the hidden structure becomes visible. One frequency may appear strong, while another appears weaker. This process is similar to passing white light through a prism and revealing the hidden rainbow inside. The Fourier transform works by comparing a signal against rotating waves of different frequencies. Mathematically, these rotating waves are represented using complex exponential functions. When the detector wave matches a frequency hidden inside the signal, strong resonance occurs and the output becomes large. If the frequencies do not match, the waves cancel each other out. In this way, the Fourier transform acts like a frequency detector, identifying the hidden oscillations contained within the signal. At first, the use of imaginary numbers in Fourier analysis seemed mysterious. However, complex numbers provide a natural way to describe rotation. A complex exponential represents circular motion in the complex plane. This means that oscillations can be understood geometrically as rotating vectors. Through this connection, Fourier analysis links waves, rotation, and geometry into a single elegant framework. It became one of the deepest and most beautiful ideas in modern mathematics. Today, the Fourier transform is everywhere. It powers audio compression, wireless communication, medical imaging, image processing, and even quantum physics. Scientists use it to study brain waves, astronomical signals, and biological data. Whenever we try to uncover hidden patterns inside complex information, Fourier analysis often appears. What began as a mathematical curiosity has become one of the foundational tools of the modern technological world.